if you were to take these charges, the outer charges, and completely remove, if I were to completely remove this charge, like that, right here, exactly, if I were to remove, if you were to make the outer charges stationary and completely remove the middle charge, what would be the electric field right here? What is the electric field right here? Okay. Well, notice that we've already calculated the force based on this a particular charge right here, Q3. But notice that I can calculate the electric field at that point very easily, because it's the total force. It will be the force divided by that charge, Q3. Okay, so I simply take, even though we take the charge out, in other words, the electric field is related to the size of the force, but I normalize, or I divide out the size of that charge. So it's as if that charge isn't there. Okay, so I'm going to get minus 9.9 times 10 to the 4th newtons, and I divide by the size of Q3, which is 0.00064 coulombs, and I'll get a number that has units of newtons per coulomb. And I'll get 9.9 e to the 4th divided by 0.0064, and I get, it's a really big number, but I get about it's a minus number, 1.5 times 10 to the 7th Newton per Coulomb. Okay, so but I simply, to calculate the size of the electric field, I simply take the force and divide it by that Q. Okay. All right, that's number 5. Okay, number 6. I have 3 charges. Now, I may not solve this exact totally, but I may just kind of basically set this up for you. It's kind of a long one, but you have a 3-charge arrangement like this. And then one over here. You have this kind of arrangement, and from here to here, this angle here is a 75-degree angle, and from here to here, this is a 19-degree angle. That tells us we're going to have to be calculating we're going to break it down to the X and Y force components. And this distance here is 0.20 meters, and this distance here is 0.40 meters. And the question is, what is the instantaneous electrostatic force on this charge right here? So what's the force on this charge? Okay, so we'll call this 1, 2, and 3. 1, 2, and 3. Notice they're all, let's see, that's a minus charge, and, whoops, that's a minus charge, that's the plus charges, and so assuming this is going to sit, well, just in this instantaneous condition, this is going to feel the force this way. We'll call that a force to F3. This is going to feel a force this way. We'll call that F1. The resultant is going to be the vector sum of these forces. So for the first step is to calculate the size of F1 and then the size of F2, and then we need to add them up in using vectors. We break them up into components, and we simply add vectors just like we normally would add vectors going all the way back to, I think it's chapter 3. So F1 F1, if you work this out, I'm just going to work it out real quickly, and it's going to be 9 e to the 9th times the size of this charge, 0.0012, times 0.0024, divided by 0.2 squared, and I get, just real quickly, 6.5 times 10 to the 5th newtons. Okay. Now, force 2 is Q3 times Q1 times R squared, and this force going this way, and that's e to the 9 e to the 9th times Q1 times Q3 divided by 0.4 squared, and I get 8.1 times 10 to the 4th newtons. Okay, so basically what I have is I have in a vector diagram, okay, that's 19 degrees, that's F1. Okay, and then coming down, it's not quite vertical. That's F2, and that's 75 degrees. 75 degrees. So I need to add up these components. So what we have is that the total, we have an x component here and an x component here. So the total, what I'll do is I'll use the method in chapter 3. Basically, the total x will be F1x plus F2x. Okay, and that's going to be going from the x dimension. It's going to be 6.5 times 10 to the 5th. That's F1. Let's see, excuse me. I got these back. There's F1, here's F2. Or I should say F3. I'm calling, okay. The first one is, this angle is all the way from here, so it would be 180 plus 180 plus 75, so it would be the cosine of 255, okay, and I'll add to that this 8.1 times 10 to the 4th times the cosine of well, if I go all the way from here around here, actually I can tell it's going to be 19 degrees, but if I go all the way around here, it's going to be 360 degrees minus 19 degrees, so it would be 341, okay? So that will equal, I'm going to 255 times the cosine, that's a negative number, times 6.5 times 10 to the fifth. And I add to that this 341 times the cosine of that, that should be a plus number, and it is, times 8.1 e to the fourth plus, and I get 9.2 times 10 to the fourth. That's the f of x. Okay, that's going to the right. Now f of y will be f1y plus f3y. Okay, f1 is 6.5 times 10 to the fifth times the sine of 255 degrees plus 8.1 times 10 to the fourth times the sine of 341 degrees. So let me calculate that. 255 times the sine of that times 6.5 e to the fifth. Okay, and then the second one, 341 times the sine times 8.1 e to the fourth plus, and I get negative 6.5 times 10 to the fifth. 345. Excuse me. 1, 2, 3. Yes. Okay. So I'm going to erase this right here. So what I have is that f of x is 9.2 times 10 to the fourth, and f of y is negative 6.5 times 10 to the fifth. The sum of these, or the force, the resulting force, is simply the square root using Pythagorean's theorem, and I'm going to end up with 9.2 e to the fourth. I square that plus 6.5 e to the 5, and I square that, and I get 6.6 times 10 to the fifth. Let's see, 1, 2, 3. That's right, 6.6 times, that's the resulting force. Okay, and this angle from here all the way to here. Okay, well, first of all, what we do is we take, whoops, remember the tangent of this angle, the tangent of this angle right here, okay, is the y divided by the x, so it's the y divided by the x. So the inverse tangent of that angle is the inverse tangent fy over fx, which is 6.5 e to the fifth divided by 9.2 e to the fourth arctangent, and I get 80, we'll call it 82 degrees. Okay, so that's this angle here, so that's actually minus 82 degrees. So the full, so if I take 360, that's in the fourth, we're in the fourth quadrant, so I take 360 minus 82 degrees, That's the same thing. So I could say it's really minus 82 degrees, or it's 278 degrees. Okay, so whoops. I get that the answer, I get about 6.7 to the fifth, and the book says the angle is 260. Let me calculate that one more time. Maybe I did something wrong. 6.5 e to the fifth divided by 9.2 e to the fourth. 82. Well, I'm getting a slightly different answer. I'm getting a slightly different answer than the book. Not quite sure why. Anyway, but you can see this is generally how we work the problem. All right. Now, suppose, okay, well, let's go ahead. Go on to the next problem. Okay, number 7. Okay. Draw the electric field lines generated by these charges. We have a +1 charge and a -2 charge, like this. Okay. And so remember, when you draw the electric field, this is just a drawing problem. This charge has twice the charge on this one. Okay, so this is plus, this is minus, but there's twice the charge over here, so the electric field lines go from here to here. Okay, so we're going to draw immediately one going this way. The big arrow goes like that. If I draw, let's say 4, you just pick a number. If I pick 4 coming out of here, then there must be 8 coming out of here. Okay, coming into here. So 1, or tell you what, I'll make it 3 and 6. If I make 3 lines coming out of here, I would make 6 lines coming into here. So I'm going to kind of make them equidistant. Notice there's 3 lines coming out of here, but there has to be a total of 6 lines coming into here, so I just kind of make them equidistant. So it would look something like that. Okay. So if a negative charge were placed in this field, in what direction would it travel, and where would it experience the greatest acceleration? If I just dropped a negative charge into here, like right here, boom, the negative charge is repelled by this charge, but it's attracted over here, so it's going to migrate right over there. Right? It's going to migrate right over there. So where is it going to feel the largest, where is it going to feel the largest acceleration? Well, it's going to be right in here, because it's attracted to here, but it's repelled from over here. Okay. Okay. Calculate. Now the question says, in this problem, okay, the separation distance from here to here is 2.5 meters. And it says calculate the electric field right in the middle. What is the electric, calculate the electric field at this point that's right in the middle. Okay, right in the middle, right here. Okay. Well, remember, the the electric field, okay, the electric field remember the force here, if we have a little plus charge right here, it's going to feel a force this way and a force, excuse me, if I put a charge right here, it's going to feel the force this way. If I call this charge 1 and charge 2, it's going to feel a force this way from this charge. It's repulsion force. This is a plus charge to the right, but it's also going to feel a charge this way, force 2, from this charge over here. Okay, so basically, one way to do it is the total force. The total force is simply the sum of the forces, which will be force 1 to the right, plus force 2 to the left. Okay, that would be the sum of the forces. Okay, and then we can actually add up what this is. It will also be K. I'm going to call this Q1, and I'm going to call this Q2, and I'm going to just call this one small q. Okay, so I'm going to say Q1 times small q divided by R squared. Now this, I'm going to let R be 2.5 meters divided by 2, which is 1.25 meters. So that's R. It's simply half the distance from here to here. Okay, so this is the force going to the right, and I add to that the force to the left. Notice Q2 is larger. Okay, and now the electric field at that point, the electric field is simply the total force divided by Q. Okay, simply divided by Q. So notice now I can go ahead and calculate the force, these two forces, and add them up, but I don't even really have to do that. It is simply, from algebra, is simply K Q1 over R squared. Notice that the Q's are going to cancel out. The small q's are going to cancel out. So I'm going to have K Q2 over R squared. Notice that this is a plus charge, and this is a minus charge. Okay, plus charge indicates a force. We're going to say a force to the right. A minus charge indicates a force to the left. Okay, so the electric field is simply given by this. So I'm going to add this 9 times 10 to the 9th Q1, that's plus 1, divided by 1.25 squared, and this is actually a minus number because this is a minus sign here. 9 times 10 to the 9th times 2, 1.25 squared. And I'm going to get, notice I can see what this is going to be. It's simply going to be, I can add these up algebraically, and I'm going to end up getting minus 9 times 10 to the 9th divided by 1.25 squared. Okay, 9 e to the 9th, whoops, 9 e to the 9th divided by 1.25 squared, and I get 5.8 times 10 to the 9th Newton coulombs, and it's an electric field to the left. Okay. Let me see here. I'm not sure. Let me see if, according to this, I may have calculated this wrong, but let me see. Or that maybe I didn't plug these numbers in right. Divided by 1.25. Okay, let's see. 9 e to the 9th divided by 1.25. I get this number as plus 5.8 times 10 to the 9th, and I would subtract from that 9 e to the 9th times 2 divided by 1.25. I would subtract from that a 1.2 times 10 to the 10th. Okay, I think I made a error over here. And if I add those together, yeah, I get minus 1.7 times 10 to the 10th. Okay, and that's actually going, it's a field going to the left. Okay, so, okay, so that would be the size of the electric field, and at that point, and it's a field going to, electric field going to the left. Now, the second part of the question is, what would the force be if I dropped, if I let little q be minus 0.66 millicoulombs, minus 0.66 millicoulombs. That is, I drop a little negative charge in here. Okay. What would the force be? Remember, the force is now the electric field divided by that charge. So it will be the size of the field. It will be minus 1.7 times 10 to the 10th Newton per Coulomb, and I multiply that by the charge, negative 0.66 millicoulombs times 10 to the minus 3 coulombs. Okay, notice this. Notice the sign. We're going to end up getting a plus force, but let's actually let's think about this. If we put a negative charge in here, the negative charge, what's going to happen? The negative charge is going to be attracted this way to the left, and it's also going to be repulsed this way, okay, to the left. And so if you put a negative charge in here, it's going to want to go in which direction? It's going to want to go to the left. Now, the electric field remember, the electric field whoops, did I have the oh, you know what? I made a mistake, because when we put in this charge, notice this is a plus charge and this is a minus charge. We put a plus charge in here. I had these things wrong. I had the signs incorrect. The force F1 from charge 1 is going to be pushing it to the right. Force F2 will be also pushing it to the right. So both forces F1 and F2 are actually both going to the right. I had the signs incorrect. If I have the plus charge here, there's a repulsion force field from over here, but field from this charge over here, there's a force to the right, directing it to the right. So both forces are additive and they both go to the right. So what that means is that, that these